So in this video, we talk about the basics of network address translation and how a network address translator, or NAT, works. So if we go back to the end-to-end principle, there's this idea, the strong end-to-end argument, that the network's job is to transmit datagrams as efficiently and flexibly as possible. Everything else should be done at the fringes. So in this model, we'll have, say, two hosts that have IP addresses, and really all the internet should do, all that the set of hosts and devices between these two nodes should do is forward and transmit their datagrams. Should send it along some route through the internet, figure out the best route, and deliver those packets between these two hosts. That's all the network should do. You want all the intelligence at the edges, because that's where the action is, that's where you can add new things. And when you start adding stuff in the middle, then you start introducing dependencies and complexities and make the world generally a tougher place. So a network address translator, or NAT, was first specified a good while ago in RFC 1631. And so NATs are a really interesting example, a really compelling example of how putting some smarts into the network can have some really, really nice benefits in some ways, have some really attractive benefits, but also introducing that complexity can cause a lot of headaches. So essentially, what a network address translator does is it's some box that sits between you and the internet, like say this host on the left. So here's our NAT. And this NAT has its own IP address for the public internet. So let's just call that IP address X. And what happens is, what a NAT does is that when a packet comes from your computer, what's called its internal address, or its internal interface, internal, what the NAT does, and that's going to somewhere out on the broader internet. So the NAT has an internal and an external interface. Is the NAT will rewrite your packet so that it appears like it is coming from the NAT's external interface. And so if the NAT, let's say it has internal interface I and external interface X, well, your packet might be from 171.64.15.55. The NAT will rewrite it to be coming from IP address X. So then the packet goes to this other host. It sees a packet from X. Maybe it's a TCP connection request or something like that. And so it'll send a packet back to X. So the destination is, here's the source is X. Here the destination is X. The NAT, on receiving this packet, will know that it was actually intended for you, will retranslate it, rewrite the packet to being to destination X to being your destination, and then forward it appropriately to its internal interface. So this turns out to have a bunch of really nice advantages. For example, almost all wireless routers today, or basically all wireless home routers today, are NATs. The idea is that you connect your wireless router to your internet connection. The ISP gives you a single IP address, let's just call it X. Then internally, the NAT can give many machines behind it different private IP addresses, just local IP addresses, and translate all of them to a single public IP address. So it's a way for a whole bunch of nodes to share an IP address. And this is what it allows you to have, say, 10 machines in your house with a single IP address, is a NAT, with a single publicly routable IP address, the NAT's IP address. Similarly, this provides some security properties where, because your IP addresses are hidden behind this NAT, it actually turns to be very hard for adversaries or attackers to start opening connections to your machine. So it's a limited kind of firewall security protection. So NATs are really, really attractive and popular. They got a bunch of great, give you a bunch of great advantages and great pieces of functionality. Now let me walk through a more concrete example with some IP addresses of exactly what's happening when you sit behind a NAT. So we have these two hosts, A and B, and they're both behind NATs. And these NATs are on completely different networks. So one of them has this IP address, 128.34.22.8. This other NAT is 76.18.117.20. So it's these two people at home, different ISPs. So the first thing to note is that the NATs are giving these hosts behind them these private IP addresses starting with 10. So if you try to send a packet to 10 on the internet at large, it doesn't go anywhere. It's considered a private local address. It might go to, in fact, you have one, to one of your private local machines. So the NATs can share these IP addresses. In fact, it's possible for a machine behind NAT B and or behind the NAT on the right and a machine behind the NAT on the left to have the same IP address, because that IP address is only valid within their small domain. So what happens now when A wants to open a connection to, let's say, this SSH server out in the network? So it's trying to open a connection. Well, this is going to result in a TCP SYN packet. Now, when A sends the message, the source address is going to be 10.0.0.101, and the destination will be 18.181.0.31. The source port, it's going to be some port that A decided on. Let's just say 5000 for simplicity. The destination port is going to be 22. Now, when this packet traverses the NAT is going to translate the network address. It's going to rewrite the network address, so that rather than coming from 10.0.0.101, the packet's going to be coming from 128.34.22.8. The destination will remain the same, the destination port will remain the same. But it turns out the NAT also has to rewrite the source port, because otherwise what happens if two hosts behind the NAT both decide to use port 5000? You can't share port 5000. So we'll rewrite the source port to be something like 8035. This packet then goes out over the internet, reaches the SSH server, which sees a request from 128.34.22.8, port 8035. It'll generate, say, a TCP SYN-ACK in response to this IP address and port. When the NAT sees that packet come back in, it's going to retranslate that 128.34.22.8 8035 to 10.0.0.101 5000 and forward that packet to A. And so it sets up a mapping between this internal port IP pair and an external port IP pair. Similarly, when host B sends a packet to the SSH server, the NAT is going to translate its IP address and port to its own, so that B's IP address to its own. So what was once 10.1.1.9 port, let's say 13,013, is going to become 76.18.117.20, let's say port 2009. So that then when the SSH server sends this TCP SYN-ACK back, it'll send it to this IP address port pair, which the NAT can translate back to the internal IP address port and pair and deliver to node B. So how does this work? The NAT is magically setting up these mappings. How is it managing these mappings? Well, it turns out there's all kinds of different ways NATs can operate, and we'll look at that in some future videos. But the basic model is that the NAT doesn't create a mapping generally until it gets a request from inside. So here we have the NAT's internal interface, and here we have its external interface. So generally speaking, when the NAT sees packets destined to the to nodes on the external interface, that is the internet at large, from nodes on its internal interface, in response to those packets, it might generate a mapping. So in this case, let's say A is trying to open a packet to server S, port 22. And so there's a packet coming in from 10.0.0.101. And let's say it's a TCP packet. And this is port, again, let's say 5000. And it's going to 18.181.0.31, port 22. Well, then that's going to say, look, I see a packet that is trying to open up a connection. What I need to do is allocate for this particular internal IP port pair an external IP port pair. So let's say 128.34.22.8 port 7009. So it's going to create a mapping from this 10.0.0.101 5000 to 128.34.22.8 7009. And this is for TCP and TCP only. So then the packet will traverse, it'll look up this mapping, it will translate the packet, send the packet with the external IP address port, then when a packet comes back from the server, it's going to look up and say, aha, I received a packet on my external interface. I'm going to see if I have any mappings which match it based on the protocol IP address port. And then if so, translate the packet and rewrite it to the internal address and port. So that's at a high level what's happening. It turns out there's all kinds of variations and all kinds of details which we'll go into in future lectures, but that's the basic model. The NAT is maintaining some state so it can translate the packets. And generally speaking, it sets up this state in response to receiving a packet from a node on the internal interface requesting or that's sending packets to a node outside. And so when you connect over wireless to your wireless router at home, this is what's happening. When you say look up on your using your network control panel and you see what your IP address is, you'll see it's almost certainly a local private address, either something in the 10 range or 192.168. And then when you're sending packets out to, say, servers on the internet, the NAT is translating them to its own public IP address and port. And so, for example, let's look at my iMac here in my office. So if I look at my IP address, so it turns out the wireless is EN1, that's the wireless interface. You can see, in fact, I have a private IP address, 10.33.6.35. So this does not go out over the internet at large. This is a local private address within Stanford. And so that IP address can't be used, say, Google servers cannot send me a packet at that IP address. So this means that I'm sitting behind a NAT. In fact, if I type, what's my IP into a Google server, it tells me that my IP address is 171.66.168.122. And so what's happening here is that I have a private IP address of 10.33.6.35 on the internal interface of a network address translation box. And the external interface of the network address translator is 171.66.168.22. So when I issue a connection request to Google servers, this is the IP address they see. And they send packets of this back to this IP address. When the NAT receives those packets, it then translates them back to my own private local IP address, forwards those packets, the connection is set up. So these are everywhere, and you should probably try this at home.